Okay, so this is an activity to work on once you are happy with your knowledge on refraction and reflection to see whether you really know what you're doing. And I'm going to do it using a PhET simulation. So that's a website called PhET, and it's a simulation called Bending Light. So you're going to want to open that simulation, get it running, and you're going to select intro mode. And we're going to make the initial material air and the material across the boundary into water. So you can do that by changing the settings. So the first thing we're going to do is describe how the speed of light will change as it crosses the boundary. Well, water is a more dense medium, so the speed of light is going to decrease. So it would start at about 3 times 10 to the 8 in air, but it'll go to a value less than that. Okay. So using your answer to that one, predict what happens to the refractive index as light crosses the boundary. Well, refractive index is inversely proportional to the speed of light in the medium. So if the speed decreases, the refractive index increases. So we can see it's the V on the bottom line that is decreasing, C is a constant, so they're inversely proportional. So what will the light do when it crosses the boundary? Well, if it's going from low refractive index to high, it's going to bend towards the normal. Well, what that means is the angle of incidence is greater than the angle of refraction. So if the angle of incidence is 30 degrees, predict the angle of refraction. So you're going to need to get the refractive indices from the simulation. You're given those. So we're going to use Snell's law. We want to figure out the angle of refraction, so we want to calculate R. So the first thing I did is calculate what sine R is by putting in the values and then doing inverse sine to give me R to 2SF. So what we can do is actually use the simulation to check that out. And when you do that, you should see that, yes, we've got a value around 20 degrees. So looking at the simulation, what other process occurs besides refraction? Well, you can see a process going along here called partial reflection. You can see the reflected ray at the boundary as well. So that's the process that you can see alongside refraction. And using the light intensity measuring device, we can see how much goes along. So this is the intensity of the reflected light ray. And this is the intensity of the refracted light ray. So you can see that in the instance, you've got way more refracted than reflected. If we increase the angle of incidence, we get a lower percentage being refracted and a higher percentage being reflected there. So the bigger the angle of incidence gets, the higher the percentage that gets reflected, essentially. Okay, so increase the angle of incidence all the way up to almost 90 degrees. Do you get total internal reflection? Why or why not? So I tried that. I got pretty close to 90 degrees, and we can see we've still got refraction occurring. We've still got a refracted ray there. So clearly we're not getting total internal reflection, and the reason why is we're going from high refractive index to low, where light bends away from the normal is what we need to get total internal reflection, but it's bending towards the normal here, so we can't get total internal reflection. So now what we're going to do is we're going to change them around. So we're now going to change material 1 to water and material 2 to air and set our angle of incidence back to 30 degrees. And we want to describe what that looks like. So let's have a look. This is what we get. So we're starting in water going into air. So we can see here that we have got light that is bending away from the normal. And what that means is angular refraction is greater than the angle of incidence. So using Snell's law, predict the critical angle for the water-air boundary. The critical angle being the angle of incidence, which the angle of refraction is 90 degrees. So first of all, it's going into air. So the second material, N2, is 1. And the angle of refraction is 90 degrees, and the sine of 90 is 1. So what that means is that the refractive index of water, the initial refractive index, times by the sine of the critical angle is equal to 1. And we can rearrange that to calculate C about 49 degrees. So let's try that out. So this is the closest I could get to a critical angle, and we can see that the angle of incidence is about 50 odd degrees in here. So it's not too far from our calculated value. Okay, so now I'm going to switch into wave mode. So what we've been doing so far is we've been imagining light as Newton did, as a stream of particles that follow the ray of the laser. So now we're going to start thinking of them like Herken did in terms of waves. We're going to look at wave refraction. So describe how the wavelength changes as it crosses from water into air. Well, if we look at this diagram here, so in air, it has a longer wavelength than it does when it's in the water. So wavelength is increased in there when it crosses the boundary. So using the wave equation and your knowledge of frequency, does this answer make sense? Well, frequency, so once you've emitted a wave, frequency doesn't change. So we know that when it goes from water into air, the speed is going to increase. So if frequency is constant, speed increases, wavelength must increase too. So that makes sense. Describe the wavelength of the reflected ray compared to the incident. Well, if we look at it, the wavelength is exactly the same, and we can use the tools to measure it if we want. So those are the same. And does that make sense? Well, you should know that the speed of a wave only changes if the medium changes, but the light's still in water. So the speed should be the same before and after. The frequency is the same before and after. Therefore, the wavelength has to be the same. That does make sense. Okay, switch the simulation to prisms. So we're going to look at dispersion now, and place a triangular prism with its base horizontal. Switch on the laser and describe the path as it crosses the boundaries. So this is what you should be looking at here, and I've drawn on some dashed normal lines so we can look at describing it. So in terms of describing it, the first boundary, it's refracted towards the normal because it's gone into higher density, and the second boundary, it refracts away from the normal because it's going into a less dense medium. Switch it to violet and describe how the angle of refraction changes. So there we go. We can see it with violet. Okay, so at the second boundary, the angle of refraction for violet is greater than the angle of refraction for the red light was. Okay, so why is that? So actually, we're going to look at the first boundary because that's got the most similarities between the two lasers. So that's where we're going to be able to explain it the easiest. So at the first boundary, they're both starting in air, so N1 is 1 in both cases. So the key here is red light travels faster than violet, and that means the refractive index for red is smaller. So at the first boundary, they all have the same angle of incidence. The red and the violet had the same angle of incidence. So what that's going to mean is if the refractive index, or N2, is lower, sine R must be bigger. So refractive index for red is smaller, so sine R and therefore R must be bigger for red than for violet. And that's really the point at which the colors separate the first boundary, and then the second boundary just exaggerates that change. Okay, so we can see it here. If we actually use white light, we can use a prism to split light up, just like Isaac Newton did. And then Isaac Newton used the second prism to put it back together again in order to demonstrate it was the splitting of light that was occurring. And you can see at the second boundary there, the violet has a much bigger angle of refraction than the red light does. Okay, so that wraps up this little simulation looking at refraction and reflection, and then finally dispersion.